right, welcome everyone to Remoticon 2020. We're very excited to have Keir with us today from Google. A few quick reminders as folks are still joining. This workshop is being recorded, but all participants will be edited out of the final version. And as always, feel free to use the chat to interact with Keir, as we also have a moderator, Andrew, to help with any questions. All right, so please give a warm welcome to Keir Mierle.
Everyone, I'm Keir, nice to meet you. And I'm here to talk to you a little bit about this new thing called Pigweed. And before we get into it, just wanted to emphasize that we're looking at the chat, and actually some of the team is here as well to help out with any issues. I think there's a good chance there'll probably be a couple challenges since we've been furiously trying to get some of the code ready to go for this, and I think maybe some of it is a little bit hot off the presses. So don't be shy and hop into that Hackaday chat, and we'll try to help you out there. Also, we're available for to talk with us later at our normal chat room, which is on Discord, and you can find that pigweed.dev. Cool. Well, with that, let's get into it. So, all right. So first off, the thing that everyone should be starting with is to clone Pigweed. Actually, before I get into this, I'm just trying to see if there is, if people are in the chat. There's the chat. Okay, cool. Yes. So this workshop is going to break into just a couple parts. So first part of the workshop is that I'll talk to you a little bit about Pigweed and why are we doing it. And then we're going to spend most of the time going through and doing some exercises to kind of try to use some of the facilities in Pigweed. And through that, we're going to build up kind of a really super basic factory test station, which and I'll go through what this is as we get there to kind of help understand the source of why did we build Pigweed. So that exercises. So we're going to put that together, and hopefully by the end of it, you'll have a little bit of code that will let you exercise some functionality on a piece of hardware that you have. And we have two pieces of hardware that are supported. One of them is the Teensy, and Teensy I think 3 or 4, 3.2 to 4 I think should work. And this, which is the Discovery board. Now, when we first started the workshop, we didn't have support for Teensy. The team has been hard at work making that go. And that should be working now. And that's actually what I'll be demonstrating on today. So yeah. Okay, so before I hop into some of the exercises, I wanted to talk for a couple minutes about like, what is Pigweed and why did we build it? When might you want to use it? And where does it fit in the ecosystem of other kind of embedded systems? And the answer to this is kind of in short that Google has quite a number of different mechanisms for doing embedded development, various RTOS related systems, but there is some fragmentation. And so Pigweed was kind of an effort to try and make an opportunity to share code among teams to just better leverage some engineering resources. So that's why when we joke around and say Pigweed's just a collection of libraries, it's kind of true. It's really just a series of middleware components. Now, a collection of libraries is great, but typically, if you're doing a new embedded project, you might want to do a little bit more than just have some additional libraries. Maybe you're starting a new project and you want to have some common big software tools like linting and unit testing and so on. And so Pigweed offers more than just libraries for things like logging, tokenization, logging and key value store. It also offers some additional stuff around general software development, which includes things like, as I mentioned earlier, unit testing, which unit testing is pretty normal on host when you're developing with a big computer, but when you're developing on an embedded device, it's not as common. It is something that's done, but we have found that it's not prevalent. And so one of the things we offer in Pigweed is unit testing facilities, and additionally, things like linting, static analysis, and so on. So today we're going to look at kind of a bit of both of these. We're going to look at the collection of libraries and see some of the facilities there, but also some of the tooling, which just kind of helps get going with embedded development, like setting up your tool chains and other such things. Yeah, so another thing I want to talk a little bit about briefly is just why Pigweed. So code sharing is one of the reasons, but another reason is that we wanted to bring some of these modern tooling things to the embedded space. And so unit testing is one thing I mentioned earlier, but there's another area that's pretty common, and we're going to get into it, which is just communicating between a host and a device for things like factory testing. So actually, so we have a few people in the chat. Yeah, great. So just wanted to get a little bit of a poll. How many people here have done any sort of high volume electronics manufacturing, where high volume we'll say is more than 100 or 200 devices? Just out of curiosity. Maybe just put a yes or no in the chat so I have a sense for who here has some of this experience. Cool, awesome. So a couple people have done some. Yeah, yes-ish. Okay, great. In that case, I think this will be some of the things I say here will probably be more meaningful to those who've spent some time in the factory, and for those who haven't, I'll try to go through some of these issues. So one of them, well, let me back up a second. So what does a typical factory process look like? Typically you'll have a device that you build. Maybe it's something like this board that doesn't really have much on it, but it might also be a device that has additional sensors or buttons or batteries and things that need to be verified. And if you glue everything together in a factory, that's not enough, right? You need to make sure that all the components work. And to do that, you typically need to connect to the device and verify that a component is functioning. And classically, in the embedded space, a lot of this is done with text-based interfaces that are human readable, which is a benefit, but can be challenging when you're scaling up to larger teams, or you're doing higher speed communication, or you want to have a more sophisticated interaction or concurrent communication between, say, logging and sensor verification. And so these text interfaces can be problematic. And so this is actually one of the original motivations for doing Pigweed, and actually some additional code that's not part of Pigweed, but that we worked on before building Pigweed. And so this whole core of bringing some of these more higher level abstractions to embedded than what we'd seen in some of the projects at Google was was a big part of the motivation here. And so you'll get to go through the process of, apparently Google needs some more factory testing. We'll go through building a little factory test station. Okay, so I'm gonna hop over to getting set up. Hopefully people have some stuff set up today. This will be more like an interactive workshop where I like for people to try to actually get this set up and work, as opposed to me just talking at you for a long time. So I think we should get into it. So before I do that, just any last questions on this area, and of course we can talk more later. But yeah, so if anybody wants to ask anything before we hop into getting it installed and getting going. Okay. All right. So what we've prepared today is a series of workshop steps. And the idea is that if we have time, we'll go through each of these and make some changes to each of them to implement some piece of functionality. So the first part is setup. And I already have everything set up, but I will create a new repo here just to demonstrate it. I'm afraid that it might overwhelm my bandwidth. It does have to download some things, but let's try it. So in short, the repo you need to clone is here.
It's at the top of the README here.
Oh, was it right there?
Yeah.
Oh, thanks.
Under repo setup.
Oh yeah, here we are. Okay, cool. Okay. And in short, you got a clone, so you need Git for this. And this sample project, by the way, is what we're hoping to turn into just an easy to get going version of, a version of Pigweed, but a starting spot that already has everything pre-integrated. Now, one of the core ideas behind Pigweed is that it's not a framework. It's not a platform. It's more like a collection of code that you can take into your existing project and use the parts that make sense for you. But sometimes you just want to start something new and you want to have everything pre-configured. And the sample project is our current version of how do you just hit the ground running. You can just clone it and fork essentially this repo and then do whatever you want with it. And it already has things set up. So that's the idea with this. All right, so we clone it. Okay, so one of the things in Pigweed that is a little different than some of the other projects is that we have this tool called environment setup, and you can see it running right here. So the sample project has this bootstrap functionality, which is implemented inside Pigweed. Now you can customize it a little bit, so you can see here. You can see here that this banner that Tony put together shows up, and yeah, it's kind of nice to put a little bit of flair for your project, so that if new team members come in and start working on the project, they get to see a little banner, and it actually serves a practical purpose, which is that if you're working on multiple projects, when you run Bootstrap or Activate, it's clear which project you're in. And what this Bootstrap does is it installs really two main components. The first one is that it downloads this package manager from Google called CIPD or CIPD. It's used for Chrome, and it has a bunch of binary packages for things like GCC, and it actually includes a version of Python as well, and a few others. Oh, I see we had a question. I cloned Pigweed repo. Let's see here. Mark, did you clone the Pigweed repo or the sample project?
Yeah, I think for doing what we're doing today, I think the sample project is the one you want because that will also pull in Pigweed.
Yeah, I had done it yesterday, and I'd already done it before you put up this page, so I had the other thing, and that's, I think, why my Teensy thing isn't working in the other install, doesn't work in the regular Pigweed.
It should still work, and in fact, I think SIFTY will even cache the downloaded packages.
Well,
but you should.
I think the Teensy core installer won't work just because the paths are different. Mark, that's probably why you were saying the path was wrong.
Yeah. It gets like a zillion, like everything is screwed up. Like it doesn't have the right path to anything. So
sorry for the confusion there.
No problem. So
sorry about that.
I just, while I have you on here, so just to make it clear, at the moment, Pigweed is not a thing separate from a project. When you have a project using Pigweed, you kind of have all of Pigweed sitting along with it.
No, that's actually not the case. So sample project is using a submodule, like a Git submodule, to pull in Pigweed. So it does have all the Pigweed there, just like another library. However, you don't have to do it that way. So you can just go in and copy the individual modules you want into your
I'd
source
rather
repo.
share it. I've got lots of different projects. I don't want to have a separate copy everywhere.
Oh yeah, I mean, we certainly advocate the submodule approach, but some people prefer to have the copies so that they don't have to deal with Git submodules. But it is designed to support either mode. Cool. Okay. So yeah, while this is still running, so first part, as I mentioned, is the SIFTY package manager, and it's essentially a binary downloader. It's using Chrome's infrastructure, and it's used by a few teams at Google. Works pretty well, and it's pretty fast. And critically, there are maintained versions of compilers for Mac, Windows, and Linux, as well as Python versions and Go and a few others that are actively updated, more so than typical, say, Linux distribution binaries or the GCC that you get with your Mac. And this lets us have kind of a sort of Docker without Docker kind of experience where we download all the little pieces and set them all up. And we're confident that the version of everything is the same. Now, it requires a little bit of fiddling because we have different versions of the binaries on different platforms, but it works pretty well, and we've been pretty happy with this so far. So that's the first part, is SIFTY. And then the next part is the Python environment. So typically in sort of big consumer electronics projects, you'll end up with a combination of native code that runs on the device and a series of scripts and tools that are written to operate, to either automate or flash or do various things with the device. And at least at Google, this is generally done with Python. And Python has one challenge, which is that it does need to have, it's sensitive to the environment that it runs in. So essentially we take SIFTY, use that to download Python. Then once we have a version of Python that we're confident is a fixed version, we then create a Python virtual environment, which is kind of like a local series of Python packages, and then leverage that. And so that's what this little bootstrap does. Now, why does it take so long to run? It downloads about 1 gigabyte of stuff. So it is big. It is not required for this to use Pigweed. You can set it up without it. It's quite a bit of hassle because you have to install a bunch of packages and put a bunch of binaries in your path and so on and so forth. But it is doable, and some teams do that. But for many people, we think this is a pretty convenient way to get going, and it will reliably set up the tools. So this is the bootstrap process. Just wanted to see if anyone been able to run this successfully in their with their cloned sample project. Yeah, so it uses 5 gigs of space because after uncompressing, it downloads about 1 gigabyte of stuff. Cool. Okay, great. And we have people on Windows. We have one person who didn't have luck with it. Okay, so Windows is a bit of a challenge. We've actually spent quite a bit of time trying to get Windows going, and it's a little bit temperamental. So if you have problems, please post in the chat, and some of the team are here, so we can hopefully try to get it straightened out. So please post a couple pastes of the error messages. Okay, cool. So it sounds like we had some people successfully bootstrapping. So that's great.
Yeah, I just noticed, Pierce, you can't run it inside Git Bash on Windows. It has to be in cmd.exe.
Yeah, sorry about that. Git Bash is in this weird world where it's not quite Linux, and it's also not quite Windows, and it behaves a little strangely. WSL actually does work, but not with the USB interaction that you need for doing some of the flashing. So if you're only doing host side development, you can use WSL. We've previously tested it, works fine. But for most of the stuff you're going to want to do in embedded, you need access to USB. So essentially, you kind of need the native version. I highly suggest Windows Terminal if you have not tried it. It's really great. Okay, so yeah, Git Bash is probably the problem there. Cool. All right, and so this will install the Teensy core. So if you're on the Discovery, you won't need this, but I'm using Teensy today. So this will take just a moment.
Yeah, how many folks are using the Discovery board actually?
Oh yeah, actually, that's a great point. Please post in the chat if you're using Teensy or Discovery. Okay, so we have one Discovery. We will have one challenge, which is that I think on Windows, we might have some issues with RPC that we were discovering just earlier today. So there might be some problems there, so I want to apologize in advance. When we get there, it might not work. Okay, cool. So that ran great. And then, so actually, while we're here, this brings up an interesting point about Pigweed. So Pigweed is using this build system. One of the build systems Pigweed supports currently supports GN and CMake. GN is a build system that probably, I would guess, nobody here has heard of. Actually, out of curiosity, has anybody here heard of GN outside of seeing the Pigweed stuff? Yeah, I'm not surprised. Yeah. Okay, so GN is Chrome's build system. And you can kind of think of GN as Bazel, but built with hindsight and designed for client platforms where there's a large variety of configuration needed, which is pretty different than the monorepo universe that most of Google's engineers work in. And so GN is inspired by Bazel, but is in fact an imperative language as opposed to a declarative one like Bazel. And it's kind of, in my view, uniquely suited to embedded, or at least these environments where you want to have very differently configured builds, and you're able to essentially run them all simultaneously with GN, which is really cool. So you'll see more of it later. Yeah, CMake is the other one that Pigweed supports. And so if you have an existing project on CMake, you can just list a subdirectory from CMake and you'll just be able to call stuff from Pigweed. But if you're going to go all in on Pigweed, I think GN is really nice. So you'll see it's pretty fast. Okay, so great. So that ran. Now compiling stuff is usually reasonably quick. And so this is showing that GN, oh, by the way, GN stands for Generate Ninja, very creative. And it's indeed quite fast. So Ninja is what's used to build Chrome, it's used to build Android and a bunch of other things. So GN targets exclusively Ninja, but offers higher level of constructs than what Ninja offers. Ninja is kind of like you think of Ninja as the assembly language of build systems. It is a very focused tool that only executes build instructions very quickly and quickly determines if files have changed so that it can do a no-op rebuild very quickly. It's also targetable from CMake, which is nice. Okay, cool. So while that's running, all right, I'm going to skip these steps. Great. Did someone have a question? No, okay.
No question. I was just saying, if you have, there's a little GN reference at the bottom of the setup page in case everyone needs it.
Yes. Oh yeah, yeah. So there's some stuff here about GN, and one nice benefit to GN is that the code is clean and pretty short, so you can just go in and hack it. I was able to make a change to GN, having not worked in the source code in a day, which was really great, or even less than a day actually. So that was pretty helpful. Okay, so this is almost done building. And actually, while this is building, I want to point something out, which is that you can see this first part here is it's called well, we call it a Pigweed target, but essentially in GN, there's these separate build environments for each of the targets. So in this case, it's building for Teensy. It's also building for Discovery, and additionally building for the host using the Mac tooling. So all these are being built in a single shot of Ninja, which is pretty nice. And so if you're doing development, you can kind of get these things built at the same time and get the benefit of seeing that, oh, I may have made something that works on my local board, but I broke the host build, and you'll see it right away. You don't have to wait until it gets pushed up into continuous integration when you make the changes. Okay, so I think this is the build, and yeah, great. All right, just looking through the chat. Great. Okay, so this list is showing some of the things that have been built. And you can see that, for example, the logging event handler has been built for a couple different targets. So one is the host, which is in my case, a Mac. Another one is the Discovery. And here's another one, unit test. The unit test library itself is built for Arduino, the host, and the Discovery. Okay, so this is basically it for build. So I'm ready for us to move on to Blinky. Before I do that, do people have questions or thoughts? How many people were able to successfully get through to running the build? Just put your hand up if yes or no, or say yes or no in the chat. Cool. I'm really glad this is all working. Nice. Awesome. Okay, cool. Still building. Okay, in that case, I'm going to flip over to Blinky, and hopefully any ongoing builds will be finished by the time we get through this. Okay, so Blinky, of course, the canonical thing to build in firmware when you're working with a new device or a new OS is to blink an LED. Of course, Pigweed is no different, and we're going to do it by going through these series of commands. So I think this is already done in the last step, but we can run this again. this was already built, but probably won't do anything. Yeah, actually, one thing to note here is that build, this no-op build, was super fast. It only took, I don't know, a second or two. And a fair number of things are being built here. So that's why we like Ninja. Okay. So this command that I'm going to paste is going to flash the device with Blinky. And I want to point out a couple things here. So first off is this Arduino test runner, which is the, we call it the target test runner. There's one of these or something like this for every one of the targets, including the discovery, the host, and so on. And this is a mechanism that lets you customize how your particular custom product is handled. And so that's why right now we don't have, for example, oh, there's a Pigweed flash script that works for everything. We don't have it because every product is a kind of a special snowflake, unique and different. And so typically some custom flashing or code or little bits are needed in order to flash the device. And so that's what this, in this case, Arduino test runner is specific to running Arduino stuff on under Pigweed. So yeah, you can see what this is doing. Oh, there's a bunch of config. We actually generate the config as part of GN. It's maybe a bit of a long explanation, so I won't go into it, but it's actually kind of interesting the way the whole thing works. And in this case, we're not actually trying to run the test, we're just trying to flash. So that's what this is doing here. And then since we're doing a multi-target build, this path is kind of long, but you can see here that for the Arduino target, there's object files, and then inside the workshop, and finally we have the Blinky elf. So let's run it. And you could also see over here, I don't know if it was fast enough for you to notice, but the Teensy flasher went active while I was doing this, this flashing. So it looked like it ran, and then, so right now the device, oh, actually we can just, cool, so it flashed, great. So before I go any further, where is the flashing command? Okay, the flashing command is here. I just paste it into the chat. Here, so if you go to O1 Blinky, and then scroll down to flash blinky.elf, this command. Or if you're on Discovery, it should be this command here.
I apologize if that the Discovery board command doesn't work. I don't have a board to test it with.
It looks like at least one person got it to flash, so that's good.
Nice.
Yeah, which is awesome. Okay, cool. All right, and we'll go through the code in just a second. So, all right. For Teensy, currently the device doesn't actually start until you connect via serial, which is something we're gonna probably change, but let me just pull up my, okay. So, okay, can people see the blinking on the on my video? I'm not sure if the video is still showing.
Yep.
Yeah, okay, great, cool. So in short, this is what you should be seeing. If you are on Teensy, it might not be working until you run the serial command here, which, as you'll see, might in fact print, and don't ignore that previous command. Oops. So this command here, python-m serial tools.miniterm raw, this is connecting directly to, in this case, the Teensy serial port. Okay, and now this looks confusing. What's going on? It's viewing gibberish. So it's actually not, and I'll go into the details of what this is doing in a little bit. But what you're seeing here is these raw HDLC packets, which is our transport over UART. Actually, you could choose whatever transport you want, but the one that we're using for the example is this. And so let me just Control C out of this. Yeah, now it turns out if you're on Teensy, you do need to run this command. If you don't, the Teensy won't actually blink. I'm not sure why it stopped. Yeah, there it is. Okay, so I see. Yes, is there a while serial semicolon in the code? Yes, there is. Yeah, we're going to remove it, but it's just there for now. Yeah, so if anyone has a Teensy and it's not blinking, try that command that I posted. Essentially, the Teensy blocks at boot waiting for the serial to come up. And so once you connect to it on serial, it will start executing. Cool, so it sounds like we had a few people who are successfully able to get the blinking. I think Pierce is stuck. Okay, yeah, sorry, Pierce, about the Windows problems. Thanks for being patient. Could not find attached device. Huh. Was it able to flash?
I had Teensy loader, like, so I tried Blinky from regular old Teensy, like the Blinky example sketch, just to verify, and like that worked fine. And then I ran the, I guess, flashing command, except I realized I was running the flashy command from the Pigweed main repository README, like pigweed.googlesource.com, pigweed sample project, that README, which is not the Blinky one. So that looked like it successfully flashed. Then running the teensy flash blinky.elf command from the link you just sent out, that failed and would not work.
I'm not sure. So you does it flash and then it, or it's just the, it can't find the attached device?
Oh, I just went back and opened Teensy Arduino and reflashed the like OEM Blinky again. This time it successfully flashed the firmware device when I ran your flash command, but I have no flashing LED. Is it hardwired to the pin for Teensy 4.0?
Oh, I wonder if that's the issue actually. Well, so once you flash, it will act, for Teensy, it will not work until you connect through the serial.
I guess, yeah, sorry. That's what I was missing. I was a little behind on that one. You're right.
Yeah, no, our bad. That's, yeah, it's just something we forgot to take out.
Tools serial monitor, board at USB is not available.
Tools serial, So when you do this, so I'm showing the...
Oh, Python M serial tools. Yeah, okay. Let's try it that way then.
And then just select 4.
Yeah, if you connect to the serial, it should blink the light as soon as you connect. But it won't until then.
No. Oh, I open a new window. I have to go activate the environment again.
Yeah, so the environment activating is something that you're kind of, there's just no good solution. If you don't have an activate thing, then you rely on people installing stuff globally, which ends up being also a nightmare. Like it's easier to debug like, oh, you forgot to run activate versus your environment is in a mysteriously terrible and unknowable situation. And who knows why random commands don't work or are using the wrong version of programs.
I literally just rebuilt my OS before Remoticon for that specific reason.
Yes. So
nightmare.
I'm glad that you understand the pain. So that's why we have Activate and take a very strong stance on not installing random junk into your computer. Since I have personally spent quite a bit of time helping many people deal with these environment problems. So we take a strong stance on that one. Okay, were you able to get your the serial to connect?
Available serial ports, not the Teensy. Still working.
That's odd. Maybe try rebooting the Teensy, or replugging it. Because this is part of the Teensy firmware, so I'm not sure. Yeah, because the serial stuff is not inside Pigweed's code. It's in the Teensy core. Okay, so I think I might move forward because it sounds like there are some other people. No, sorry, Alex, but I think we probably should move forward. Maybe somebody from my team can help out. There's a few people who work on Pigweed here in the chat. Okay, cool. All right, I'm going to move forward. Yeah, so. Great, so you can see this is spewing some output, and it's a little bit unclear what this is doing, right? What is this sending? So in short, it's sending packets, and you actually see in the output here, the tilde character is in fact the packet delimiter. Kind of think of it as like a curly brace in something like JSON. And then the first part here, in this case, is actually our tokenized logging, and then this last bit here is basically the CRC for the message. So we have some error checking. So that's what you're seeing here. So it's not really that incomprehensible as you might think. If we didn't have tokenized logging, it would be a lot easier to understand what's happening. Okay, so let's actually decode it. So yeah, so we have. All right, so now here, I'm going to jump ahead a little bit. We're going to see more of this in the next exercise, but we can. Okay, so this command I'm running, I'll talk about in a moment, but in short, it's connecting to the Rpc service and using okay, so we're going to go back to this command in a second. And this command here started up the serial connection, which is also, in addition to handling RPC, which I will talk about, is also putting logs to a file. Okay, so let's see, is this still going? I'm not sure why this isn't following. Okay, so I'm not sure why this is not tailing, actually. This is odd. Okay, well, for some reason, this is not working right now.
Can you just tail the log file raw? See if anything's going through.
Yeah, let's see, good point. It appears not.
Maybe disconnect the Teensy and then start it over.
I don't think this is a Teensy because yeah, so this is working. But okay, we can try it. While we're trying to figure this out, one thing I want to mention is kind of cool. So our Teensy support is pretty new, and the way it works is pretty interesting. It actually downloads the Arduino installer and uses the metadata for how Teensy and Arduino works to actually generate the build files for GN, which is kind of interesting. So it opens up the door to supporting a lot more Arduino devices than just Teensy. So that's kind of an interesting little tidbit. Okay, so this is working. This is odd. I'm not sure why this is not sending the data. Okay, I'm not sure why this is not working. I'm going to move forward. But in short, what I want you to take away from this is that the logs are coming over through this HDLC mechanism, and they're tokenized, which is kind of an interesting concept. So let me pull up some code and just show what this looks like.
Keir, I could demo it if you want.
Was it working for you?
It was.
Okay, so this code here is a pretty typical blink loop. And it just initializes board LED and then does this log command, which is behind which there's a bunch of machinery. Turns an LED on, waits for a second, and then turns it off and does it forever, indefinitely. And this is also it's bare metal, so there's no RTOS here. The interesting thing is that this blink high, this text here, is actually never in the binary. So I can show you what happens. In short, these strings are tokenized into an identifier, a 32-bit hash, basically. And you can see that here. So actually, let me just make this a little bigger. Yeah, so in this case, there's actually a few other things in here, but this file, tokenizerdatabase.csv, is showing all of the different strings that are logged in the binary. And you can use the separate program to decode these tokenized logs on the host side without having to store them on the device. And this is one of our kind of flagship pieces of functionality in Pigweed. It works by using stable tokens that don't change. Even as you upgrade or modify the binary, the tokens will only change if you change the log string. Now, the plus of this is that if you do a lot of logging, which we do, we think logging is a really important part of embedded development, you get to remove these strings from the binary. This both makes it faster to execute. You don't have to format the log. It makes it smaller in Flash, so the strings are not in Flash at all. It makes it smaller in memory for things like buffering logs or having kind of a log ring buffer where you can keep track of all the logs that you've done in the past if you have to hold on to them for some reason. So that's what's happening here. And if you look at this output that we were watching earlier, these are tokens. And the $sign is just an indication that it's a base 64 encoded token. The equals is just the terminator for the base 64 encoding. And then this part here is the actual token with any arguments attached. Now in this case, we don't have arguments to these. But this one is probably blink high, and the other one is probably blink low. So if I had to look at it, you know, this plus is probably a higher bit, so probably this one is this one, and this one is probably this one. So just out of curiosity, has anybody in the talk kind of worked with tokenized logging systems before? We've found this to be critical for some products in order to make them economical, because you can save so much on flash if you log quite a bit. Yeah. So one of the things that we're not going to have time to get into too much today is that with tokenized logging like this and some of our kind of additional RPC stuff that we'll go through, we'll be able to get our log buffers down so that typical log messages only take 10 bytes. And that will include things like the timestamp and the level and a few other things in order to enable runtime filtering, but still storing kind of lots of log messages locally, which is really cool. So we can talk more about that another time, you know, maybe not today, but it is a pretty nice facility. Yeah, the deterministic message size is really nice. There is a caveat to that though, which is that you can see here, oh wait, I guess there's none in here, but if you have a %s, so something like this, let me just show you an example. Let's say you had preview log info. Let's say you have a runtime string log. So let me just pull this over here. So the log tokenization works on the compile time strings. But if you embed a string inside your log, like here, suddenly that can potentially blow over all of the size issues. So if this is generated at runtime, or you know, it's generated from like a switch statement or something, it needs to be put in literally. So it's still possible to have large log statements even after tokenizing if you use a lot of string arguments. But other than that, most things are pretty small, which is really nice. How do you end the gibberish output? Control right square bracket. It should get out. But it sounds like it's working, so that's good. Okay. So I'm still not sure why this one was not working here, but we can move on past Blinky. Yeah. Okay, so next up, we're going to do testing. And as I mentioned earlier, one of the ideas with Pigweed is to make it easier to unit test on embedded. Personally, I have found the best way to ensure that your product has not very many unit and automated tests is to make it hard to write those tests. If there's no framework for doing automated testing, you're not going to write tests. So in Pigweed, we just wanted to make testing so easy and so natural and so baked into the development process that there's just no excuse. It's just very easy to, and not just easy, enjoyable and fun to do automated testing. We feel really strongly about this. This is why you'll see there's a bunch of tests in Pigweed and generally pretty high coverage. We think the best way to make reliable software is just catch all the bugs at the lowest level you can. And sure, you'll still find things in integration and manual testing, but hopefully by the point that you find a bug in an automated, in an iteration test or a manual test, you can be pretty confident it's not an issue with the pieces, but in fact, an issue with their integration. So I'll take you through basically how this works in Pigweed. All right, so yeah. Okay, so
Keir, when you're copying stuff, just triple click on the line.
Oh, okay, cool. All right, so this is showing, it looks like a lot of output here, but this is, I think, actually, let me just, all right, I forgot this one has been tokenized. Well, it appears that we are having some issues here. We did add some of this functionality just before the workshop, so it appears as though some of this is not.
Are you using the same log file in both commands? That might be it.
Oh.
Maybe just delete it.
That's the problem.
Well, you set it to out instead of input on the RPC console.
Yeah.
Oh, that's right. You want it out there. Never mind.
You're in different directories.
Yeah.
There's work/workshop and work/.
Yeah. So I had a bunch of this stuff prepared, and so I started a new one just now. So that was the problem. Sorry for this, everyone. Okay. Okay. All right, great. So, yeah. Yeah, cool. And also, if you might have remembered that the packets previously looked big, and it's actually because this is doing some string formatting that's runtime. Okay, cool. So this is the test executing, and let me just pull up the code for that.
So that was actually just a demo. It's not using the test. And we could flash the test. That would be a good thing to do next. That uses basic logging, not tokenized.
Yes. Okay, let's do it. Let's see, where is the test? Okay, so we're going to flash the test next, which doesn't have. So this version of the test. Oh, maybe there's nothing on this one.
Oh yeah, you don't want to use a serial runner. You just want to use the Arduino unit test runner. There you
go. Okay, cool. All right, so
like take out, if you have flash only in there, remove it. That way the test runner will show your test output.
in fact, it was working. Okay. So by the way, we don't actually use the code like this very much. So you're seeing the kind of underbelly of how things work. And so there's a couple of different layers. But in short, what this command does, and I know it's a little bit long, but basically Arduino test runner, it's using the configuration that we generated. And in this case, it's saying, okay, we're going to run this test. And the runner is expecting that the test binary has a certain behavior, which is that it'll wait for an attach, and then it'll start executing the unit test. But more than that, the test runner kind of takes over. It's not expecting somebody else to connect to it in this case. And it will connect, listen for your output from the test running, and then parse it to determine pass or fail. In this case, you can see the output, and it looks very much like Google Test on host. But in fact, these strings are all generated on the device. And I can pull up the code for that right here. So this is the code. Let's see if this is working. Yeah. I'm about to tell you about this thing called PW Watch, which is kind of cool. Okay. So if any of you have seen Google Test, this syntax is probably familiar to you. So I want to point something out here that's kind of interesting. So what is this? What is this thing called PW Watch? So if you're used to using IDEs, sometimes the IDE will automatically compile your code for you, and that's great. A bunch of us in Pigweed don't really use IDEs. I mean, they're also popular for Pigweed users too, but sometimes you don't want to have to use an IDE. And so we built this little watcher thing called PW Watch, and the idea is it will help you run tests automatically. Now, in this case, something interesting is happening. The watcher is detecting that something changed and rerunning the build. The build is running tests on the host, which is my Mac, and compiling for the device. So it's not running the on-device tests. It's just compiling them. But you can see here that the test is failing as expected, right? We have a line here that will not succeed. And if I change this to a 1 and save, you can see that it will run again, and then it will pass. So this is kind of cool. But I brought this up because I actually wanted to modify the on-device one. And first off, we can run this just to see that it should pass. It's doing the flashing, it will run, it passes, okay. And now I'm going to change this to a 0. Now, of course, the host one is going to fail, as expected, right? So this is the host one. Let's see what happens on the device. Oh, am I in the right place? I am not in the right place. I'm currently paying the price for having a parallel version of the repo checked out here.
The tests, is that what you're trying to flash?
Yeah.
System stat tests. So the target's out Arduino debug tests.
That's changed.
Yeah, there you go.
Okay, so this is going to run, should fail. Yeah, great. Okay, so you can see here that this is now failing. And note that the output looks pretty much the same. So we actually have the same unit test code running on both host and device. Our test framework is compatible with Google Test without support for mucking. Unlike Google Test, ours is maybe 10 kilobytes or less of flash. Google Test is like 200 kilobytes of flash or so. So you can fit PW unit test in most projects. Maybe not the case for Google Test. Cool. Okay, so it looks like, oh, thanks for the fix for the discovery line. Maybe we can go get that fixed up. All right. Okay, great. So this is showing the unit test on device, but I had to take an extra step to flash and make it run. So what I'm going to try doing now is show how to run it automatically with watch. So let me. The way you can do this, and oh yeah, this is here. Cool. So in short, so GN, when you run it, makes an out directory. Inside the out directory is a file called args.gn. That file is basically what configures the commands. You can kind of think of it as similar to the CMake cache. And in short, this one, PW Arduino use test server, should be true. I think there is a corresponding argument for discovery. I think for discovery, it's just this use test server. Okay, so I'm going to comment this out for mine. So you need to set that. That will turn on the test server. Okay, but you need an additional thing, and we don't have time today to go into why, but there needs to be a separate server to actually run the unit tests on the Teensy itself. So the way this works is that the Ninja build will trigger not just building the firmware for the Teensy and the firmware and the test for the Teensy, it will also trigger flashing the test to the Teensy, running it, seeing that it got the result that's expected or not, and reporting the results, all part of the Ninja build, or all as part of the build. So yeah, so the first step was to turn on this, this command here for Teensy users. And I believe it is this one for the discovery users. Yeah, oh yeah, and for people on Windows, yeah, I'm sorry about the problems. And we spent a lot of time on the Windows one, and we still don't have it bulletproof. So yeah, sorry. Actually, if somebody is interested, we would love help with Windows. The problem is right now, none of us are full-time Windows users. And so we end up with just kind of little problems that we don't notice. Even though we have Windows running in CI, CQ, there still ends up being trouble. And it's just hard for us to detect all these things when we're not on Windows ourselves. We even have Windows machines and we do use them. It's just not our primary development. So if there's somebody that has a lot of Windows experience, and I think PowerShell is something that we just don't really know very well, would love help. Okay, so args.gn, so the next thing that's needed is to have the test server running. So that's what I was mentioning earlier, that a test server is needed. And what the test server does is it serializes access to the hardware. Now, in the case of Teensy, we currently don't support running the Teensy devices in parallel. For the discovery, I don't have it working right now, but we actually support running multiple discovery boards in parallel to have a little discovery cluster to run all your tests in parallel. It's pretty cool. It runs a lot faster actually with 2. It seems like it's faster than twice, but yeah. Okay, so I ran this little test server here. And by the way, if you're on Mac, and I think maybe on Windows, you have to allow this because there's a local connection. It's using gRPC to communicate between processes. And so that's what this is doing. And so essentially you run this server command and it just sits here. So Arduino test server is using the configuration that was spit out in this file, found one device. So it found this little Teensy that I'm holding here. And it is now waiting. So you can see here there's a worker waiting. And the command it's going to run, you can see is this one. So it's going to run config file with all these settings that we know about. This, it detected the serial port. And when I run commands over here, so I'm going to trigger this again. And I think this should work. Aha, okay, cool, so it's working. So what's changed from last time when we ran without the server? What's changed is that instead of just one failure, this is the failure we saw before, local on a Mac, we have an additional one, which is right here. So this is a failure on the device through the test server. And I didn't really have to do anything to run it. Well, I just started the test server, but it was done naturally with the rest of the build. So let's make this pass again. And so GN is going through, right? And actually you can see here that it ran this. So in fact, I can show this again. Let me just, let's just add a passing test here. So I'm going to clear out these lines, but there's nothing there. I'm going to save. Note the only thing I'm going to do is I'm going to hit enter. You can see the changes detected. And then right here, you can see these 2 lines. So it just executed a single test that changed and then finished running it and reported back to, it reports it actually back to Ninja, which declares success. And there's a little stamp created for it. There's a few things that are kind of cool about this. So the fact that it's integrated with the build means that it only runs the tests that change. So there's actually a few other tests in here as well that are not listed, but if you modify just one test, it will only rerun that test. Or, and this is the part that makes it really powerful, if you modify a library, and that library is used in, say, three tests or 3 executables, or the library has transitive dependencies where a core library like an assert library is used in, say, a ring buffer library, and the ring buffer library is in turn used in 5 tests. Changing that assert library will trigger just the test that you need to verify everything working, which is really powerful. It just makes the dev cycle really fast. So yeah, so that's kind of the watching thing. Now we're kind of running out of time, so I was thinking I would actually skip over the rest of this exercise just for those who are interested. I'll tell you what we were going to do, which is in short. Let's see. There's a function here that generates a status using string builder, which is one of the random libraries in Pigweed that's pretty useful. Fun fact, very easy to get null pointer errors when you're doing strcpy and other such operations with strings in C. But if you use the C++ primitives, IOStream and string stream and so on, you can just blow out your binary size, no problem. Just pound include IOStream immediately triggers a 230 kilobyte inclusion. And of course, that's completely unacceptable for most embedded products. So instead, we have a facility called String Builder, named here with string buffer because it actually includes the buffer, that does no allocations, like most of Pigweed, no allocations. And you can see here that it does kind of look like a stream, but internally it doesn't allocate. It's a little bit simpler, and it formats it. So what we were going to do with this test is verify it, but I'm going to skip it. So before I move over to RPC, which is I think one of the highlights, and I want to make sure we have a little bit of time for it, did anybody have questions so far? Or also, what do people think? Like, is this something that looks interesting or fun to work with? Yeah, the test server functionality, we're pretty happy about it. It's been a real nice, a really helpful thing especially for development. Yeah, integrating that with the test execution, just the whole package is pretty nice. Yeah, let's see. Trying to build Ninja stuck stamp. Huh. Yeah, so actually, it's a great point, being able to test things quickly on the host. So the other benefit of being able to do things on the host is that if you're making complicated logic, you could just disable momentarily running on the device and pound include IOStream and print stuff out or do whatever you want. Do your debugging and then turn it off. Or you can use host side GDB, which is just easier to use than having to go through the hassle of connecting your JTAG and dealing with all that business. And the reality of doing embedded development with Pigweed that we've experienced over our time working with it and some previous projects at Google is that, frankly, most of the time our code, we develop it on the desktop, it works the first time on the device and has no changes, just because we spend so much time developing all the unit tests. And so you just don't need the debugger that much, which is the other philosophy we have. Don't use the debugger. Use the debugger only if you really have to, but favor unit testing and high quality logging before debugging.
That was actually one reason why we decided to go with Teensy's as like the first board to support. Like, they don't have the hardware debugging facilities built in. But
yeah.
I mean, having some good logging and a nice way to run tests is really helpful there.
Yeah. Yeah, so we've really had a good time developing this. All right. Okay. Oh yeah, and I wanted to add, like, unit testing on embedded, there's actually nothing special about it. I mean, it's just like any other unit test. The only challenge is maybe you don't have access to malloc, or you can't create threads, or you can't use too much memory. But really, there's nothing special. It's just that typically you need some additional like framework and machinery in order to kind of flash the device and trigger the test running and get the results back and parse them and all that kind of stuff. But it's not that much work to put it in place, and that's what we have here here in Pigweed, and we did the work, so you can just benefit from it. Just use it. Yeah, it's very controversial, by the way, that debuggers should be a last resort. But I mean, I personally feel pretty strongly about this. Like, you're better off focusing on fantastic unit tests, really high quality logging, metrics, and instrumentation. Those are durable assets that you can reuse in the future across products, in the field, and over again. But that debug session that you painstakingly put together, the watch point and add the little breakpoints to carefully track down, and then you single step through, that's an ephemeral artifact. It's gone once you're done debugging. But logs and metrics and unit tests, those are durable assets. And so that's one of the reasons I think it's just strategically better to focus on that and kind of debug as a last resort. What about unit testing stuff that can only happen in hardware? Well, that's the idea with this, is that everything can be tested on the device. I mean, that's the whole idea. So if you can't do some of the things on the host, you have a couple options. So one option is you make a simulated device. So you can make, in this case, there's an LED, blink LED thing. And I think the host one just prints the standard out as a blink. So that's one possibility. So how does Pigweed deal with target-only facilities? That's actually a great question. So Pigweed is ultimately just a library, a series of libraries. So just like in normal embedded development, you can have defines or things like that that are different. So no different here. The place where it's a little bit ugly, and this is something that frankly we don't have completely nailed down, is things like target capabilities, where you can say, oh, my target has 100 kilobytes of RAM, or it has a megabyte, and maybe certain tests can only be run with certain amounts of memory. So we have a plan for how to do it. We just haven't implemented it yet. It's coming. Let's see. Yeah. Is there a facility to mark stuff as not host? So yes, there is a way to do it. It's not, you basically say, if it's not the host, build it. And I think I can give an example of that.
So one approach we use pretty typically inside of Pigweed is when you set up a test that won't build for host, is when you set up the thing that triggers through to building it, you only put that in the device side tests. You don't set it for like, test, all tests, which, gets picked up by host and device. And
yeah,
you can set it just to be, you just only include it for doing it on a device test.
Mark, if the Blinky command runs but doesn't do anything, so I think as we mentioned earlier, you have to connect to the serial to basically start the device on Teensy. It's something we want to fix. But so if you run that python-m command, oh, does the host run? Oh, okay. Yeah, I think we haven't actually, there's no reason it couldn't. It could just print or log something. I don't know if it's implemented though.
So we have the LED facade, and it has Arduino and STM32 and I think host implementations.
Oh, cool. Okay, yeah.
But so we were expecting it to output emojis for a light on or off, but maybe it's not doing that.
Yeah. Okay, so I want to, but these are great questions, by the way. Yeah. Okay. Yeah. All right, cool. All right, so I'm going to move on to the next one, which is RPC. And I think in practice, we're probably only going to have time to do this one. So yeah, as often happens, we're a little bit too ambitious in the amount of things we'd be able to cover. So sorry about that. But as I mentioned, we're available in our Discord after. So, okay, RPC. So actually, before I go any further, has anybody, oh, where do host build blocks go? They should, if you're using watch, they should just be displayed there. Ninja's pretty terse. It doesn't really print anything, which is not actually great, but okay. Yeah, so RPC. So RPC, you can think of this as
the host build will, if you fail the test, it'll dump them out to the console. Otherwise, it masks them on the PW watch on the success case.
Yeah. Okay, so I see. Yeah. So RPC, what's RPC? So the idea with RPC is that I just want to trigger things on my device. Maybe I want to turn an LED on. Maybe I want to access the logs. Maybe I want to flash it by sending it data. Maybe I want to download the latest version of the sensor data from the device. Maybe I want to set the manufacturing date. Maybe I want to set a calibration value for an ADC or something like that. So there's kind of a million different ways you might want to use remote procedure calls. And Pigweed's RPC system is modeled after gRPC. So actually, before I go too much further, if you have heard of gRPC, please say, I've heard of gRPC or no in the chat, just to help me kind of understand. Okay, so we got one person who's not seen gRPC. Two people, okay. One person, so 2 out of 3. Okay, sounds like most people have not seen gRPC. All right, so there's a few things here that might be new. In short, you can think of gRPC as one implementation of remote procedure calls where you have kind of an interface definition language, which in this case is Protobufs. Now, actually, before I go further, Protobufs, yes or no? Have people heard of Protobufs? Yes, okay, got a few yeses. Heard of Protobufs, haven't used them, okay. Cool, okay, all right, well, we got a couple people. So Protobufs are a binary format for structured data. You kind of think of it as a struct encoding. And you can store similar data to what you might store in JSON, but unlike JSON, it's binary, and also there is a schema. So yeah, and arguably almost all data at Google is stored in Protobufs in some capacity.
Here's an answer from Google.
Oh. So what you see here on the screen is one example of a Protobufs definition. So this is saying, all right, there's syntax is Proto3. There's been a couple versions. The package is foobar, and I'll show you some code for the Remoticon that does this. There's a request struct, which is empty. Oh, okay. I see we have somebody who has spent lots of time with this. Great. A request response, and you can see the response has a number. And then in this case, and this is where the RPC component comes in addition to these structs, you have a service that has called methods on it. So the idea is that your service might be an LED service to turn on or off, and you can send data to the service to a method to get something back, or maybe cause a change, and the response will include some additional structured data. And these can be nested, so you can have structs and structs and so on. Okay, so yeah, so that's kind of the idea here. And just to kind of give a little bit of background, I think it's often the case in embedded that this is done with sort of text mode command and response systems. And that is a pretty typical and relatively easy to understand solution in the embedded space. It's compact-ish in code size, and it's simple, but can run into some problems as you scale your embedded device up, as you have larger teams of people and you have potentially concurrent communications happening, as you have increasingly rich communications with multiple different bits of data for each request and response. Maybe you want to send back a stream of responses concurrently with other ones. And the moment you get into that territory, it gets a little tricky to do it with kind of ad hoc text protocols. And so that's kind of where the need for this comes from. So what I'm going to do is kind of show you how this kind of works, or show you an example of this working. Okay, so I started a simple RPC service, and realistically, we're not going to have too much time to actually build this out, but you can see here, this is a service. The package is Remoticon, and there's a request and response, stats request and stats response, and the response is the number of loop iterations. Now, I'll talk about that in a moment. You'll get to see what that is, what that actually means. And there's a service that has just one method, getStats, and that's it. So let's see if we can make this actually work. So first, I think this should already be built. Yes. All right, so I'm just going to flash this. Where is this? Okay, so I just got this flashed. So this example is going to show the device actually, let me just pull up the yeah, here we are. Okay, so after you flash, which is what I did here, flashes the RPC example as is. The next step is to connect to it over the HDLC channel. Let me just fix the port here. So this one doesn't automatically detect yet. Oh. Okay, cool. All right, so before we go any further, I just want to see if people are able to get this to run. So there's a couple moving pieces here. Great, okay. So whatever problem we were having before with the following, that's working. Great. So once this is built, the thing to do is flash the binary, which is this command here. So I'll just paste this into the chat. After you flash it, you need to run the RPC interactive console, which is this one here. And then the next step is to connect to the log file. Now, right now, there's a lot of commands needed to do this. This is something that we're working on improving. The reason it's like this is that Pigweed is designed to be sort of like Lego blocks that you can reconfigure and use in a few different ways. This is very nice if you have an existing system and you need to plug Pigweed into it, which is what it's designed for. But it means that if you're just starting and you want to put things together, it might require some additional work. So we haven't yet built all the integrated stuff just yet. Okay, so was anybody able to actually run this these commands and get it going? Any luck? I see some silence. If there were problems, that would also be useful to hear as well. Okay, well, put it in the chat if you, Oh, okay. Well, here, you should be able to get caught up because there's not really any change in the code. So Alex, if you want, all you have to do is you should be able to just run this command to flash. So that flashes the RPC example. And then the next step is to run the interactive console. Which is the one I'm doing here. And then step 3 is to run the detokenizer. Okay, so yeah, why don't people give that a shot? Because I think this is one of the more exciting parts of Pigweed is the RPC stuff, and I love to get people a chance to play with it. So I think this is worth spending a couple minutes on.
If anyone needs additional commands, they're all in the RPC section of the workshop README.
So if the serial port is busy, it could be that the test runner is still in the background holding on to the serial. So if you have the Arduino unit test runner hiding off in a terminal somewhere, that can interfere. It's actually something we want to fix, but for now, you need to be a little bit careful about it. Yeah, okay, cool. All right, well, let me just get this going. Okay, so while people are trying to get this going, and yes, Control-C after flash. So what I want to highlight here is that this is calling this function called getStats from the proto file. So this is this kind of command facility in Pigweed where you define an RPC service just like you would if you were building a internet service or a web service that serves commands by request and response with these protocol buffer messages. You can do the same thing on your embedded device. And so that's what this is showing here. So this little command prompt is it's actually just interactive Python. So what this is doing is it's connecting to the device through serial. It's parsing these HDLC formatted packets and then using the Pigweed RPC infrastructure, which just needs a kind of packet in, packet out interface to allow you to interact with the device. And so this object here, RPCs, this is the collection of services that are available on the device. And in this case, you can see there's actually two services. So one is the Remoticon Superloop, which is the one here. And then the other one is Echo Service. It's this one that lets you send a message and then it will echo it back. So in RPC systems, so yeah, so you're first writing code, you write a hello world with a print. And then when you're doing embedded or hardware, your hello world is the blinking light. But with RPC systems, the hello world is the echo service, which is that it just sends you back what you sent in. And so that's what this is. So the echo service is just one of the services inside Pigweed that you can include if you want to test out the RPCs. So, okay, cool. All right, awesome. So you got the tailing log, Alex, sounds like. Were you able to run these commands here, these echo service? So let me just put this into the Zoom chat. Is anybody able to run the RPC? Yeah, so actually I want to point out that it's IPython. So all the tab completion goodies should work. You know, you have all the nice things. Syntax highlighting even. Yeah, which is pretty cool. See all the stuff here. Echo service. Oh yeah, okay, I guess here. Okay, cool. So this kind of shows the functionality, and I wanted to also point out this is running in bare metal, and there's a loop that's kind of doing both blinking. Oh, actually, let me show this. It's actually blinking as well. So it's blinking while handling RPCs. All right. So any questions so far? All right. So next up, I want to show the C++ code. So you can see it in the example, and I'll just walk through.
Keir, maybe you want to get into this later, but why? Maybe you can give an example of why you'd want to send RPCs, like from the host to a product.
Yeah, so the classic reason you'd be doing RPCs from the host to the device, at least for high volume electronic stuff, is in factory tests. Now, actually, this RPC system is designed to work also in the field in consumer hands for communicating between microcontrollers, or say a microcontroller and a phone and other possible situations. But the classic one that we originally started designing this for was for a factory test. And the example is perhaps you want to turn on an LED to verify that it works in the factory. And you would have a command where you send something that says turn on the LED, and then a sensor, so the factory would have a test station that looks at the LED, or maybe it's a person, maybe it's you, you're doing a small run of devices, you want to check that the LED works. And so maybe you would have a command that turns on the LED and says, oh, do you see the LED on? You'd hit yes, and then it would turn it off and it would go on to the next test. So that's one example. Another one might be, again, in the factory, you're manufacturing, you plug the device into the first test station, and you want to write things like the manufacturing date and the serial number to the device. And so that's another case where you would use an RPC. So those are some examples. Other cases include things like maybe there's crash handling. Actually, something that is in Pigweed is crash handling, where at crash time, perhaps a little bit of flash is used to store the CPU state in order to look at it later to understand what happened to the device. And so maybe there will be an RPC to download those crash records so you can look at them later. So I think that's a few examples of where you might use RPC. Yeah. Thanks for the command, John. Sounds like our instructions might have been slightly wrong, so sorry about that. Cool. All right, great. So so this is the kind of user experience you see this here. Actually, I want to point out the RPC has a status, and this message is what's returned. But the other one is superloop get stats, and you can see here if I call this, the number is going up. Let's take a look at the code to see what this is doing.
If you get some interference on the serial line, is there any kind of error handling?
Yeah, so one of the nice features of this whole setup we have in Pigweed, which is it's all optional, but the serial handling includes CRC checking. So if there's a blip in the serial line, you will know on the host side, you'll know that something went wrong. And also on the device side, if there are corrupt packets, it's detected and ignored. Or if you can keep track of it or put that. Actually, one of the exercises in here is to track errors. So yeah, and that's a really nice feature that's possible, but a little bit harder to implement if you have a regular text mode kind of human readable interface. Is that it's just not practical, or it's just often not done. You just kind of have text interface over a UART. There's no error checking or correcting, and it's just that it is what it is, and things will sometimes fail mysteriously, especially under load. And at least with this approach, because we're able to take it over and go binary, these types of errors just don't happen as much, or at least if it does happen, there's no mystery. Okay, so I'm going to start going through the code for how this works, and there's a couple things I wanted to point out. So first off, PW or Pigweed in general is this modular stack. There's a bunch of different pieces. They're loose-ishly coupled, and you're supposed to be able to just take the pieces that make sense for you and plug them into your existing system, including your existing build system. And RPC is no different. So the way this is set up in the demo on the Teensy is like this. So in short, you have a UART, which is the physical pins. Now, of course, okay, on Teensy, it's actually UART flowing over USB, but we'll ignore that for the moment. UART is then put through this thing called PW sysIO. You kind of think of sysIO as Pigweed's stdio. It's just like standard in and out, except it doesn't use file descriptors. And you can see the module docs for that if you look it up. And then over sysIO, we flow HDLC, which you can kind of think of as just a packet framing mechanism. It's just a way of converting a byte stream into a packet stream with some error checking. That's all it does. And then on top of that, we have PW Rpc, which is the thing you're looking at on the screen, where the Rpc system expects packet in, packet out, and then all the rest of the Rpc stuff happens with just that. So before I go forward, does this kind of stack make sense? Has anybody any thoughts on this? Has anybody dealt with unreliable serial before? Okay. Yeah. Oh, cool. Well, we actually hadn't seen HDLC before. It was new to us, so it was recommended to us by some people in our extended family of embedded hackers at Google, and turns out it's a great fit. So I'm really glad we decided to use it. It's really nice. HLDC. Yeah, I'm not sure.
Yeah, it's HLDC, at least according to Wikipedia.
Really? Do we do this wrong everywhere? Wow.
Or, well, no.
Okay.
I guess you could go either way. High-level data link control.
Huh. Oh, I think that the first L is.
It's link.
Anyway. Yeah. Okay. Yeah. So let me just go through briefly how this is hooked up. So we have the sysIO writer that takes over the sysIO interface and converts it into Pigweed's kind of writer interface, which is just essentially just a callback with a write data function. And then we have this thing called a HDLC channel output. So this is the magic where the RPC system is connected to the HDLC packet in-out interface. And what's cool about this is that you could use your own. So sometimes people have a SPI bus that works differently, or they have maybe they're running over Ethernet and they're sending Ethernet packets. You would make an Ethernet channel that would bridge between RPC and Ethernet. So this is where you would do that. And in this case, we already have a implemented solution for this, which is the HDLC light RPC channel output. And that's what this is. So additionally, some devices will have multiple channels. So maybe you have a UART that you want to do RPC over, but you also have a SPI bus, and maybe there's even a low-speed Bluetooth connection that you also want to run RPCs over. So PWRPC supports simultaneously having RPCs from all of these sources, where each one of them is a separate channel. So that's what this would let you do. In this case, there's just one channel, which is the one over serial, or HDLC over serial, and so that's it. And the next up is this, which is the actual RPC server. So this RPC server is the object that holds all the services and the channels and does the actual work to kind of route packets between them or call the RPC handlers as appropriate. And then finally, these two are the, this is just the input buffer where we're pulling packets in while we're waiting for a full packet to be input. And then this one here is the HDLC decoder that kind of holds on to bytes as they come in. And then when a packet end byte comes in, it will verify the CRC and send along the packet to RPC. And you'll see how that works below. Okay, now this part, this is one of the things that I think makes Pigweed's RPC really cool, is that it's just like gRPC, and you can declare services that are in shared libraries that can be included in other projects. So the example here, Echo Service. Echo Service is in Pigweed upstream, but what we've done here is include it in our binary as just a component that you stick in, register it with your service, or register it with your server, and you're good to go. And this could be controlled with an if-def or an if to decide whether or not it's registered, which makes it pretty flexible. So you can have one binary, or you can control or whether or not these services are available. And then this one, so this superloop service, this is the one that you saw in the other file, is the one that lets you control or see how far, how many iterations have been made for the superloop. And you can see here, we have the call to register the services. So this is where they're stuck into the RPC server. Okay, so before I get into how the RPCs are actually handled, I'm going to hop down to the loop, the super loop. So how does this whole thing work? In short, forever, it blinks the LED, which is actually a little bit more complicated than you might think, and I'll get into that in a minute. It pulls one byte at a time from UART, and then if that byte is a packet finisher, so packet's complete, it will send it over to the RPC system to be handled. And then finally, it increments the superloop iteration counter, which is what's happening here. So you can see this number that's incrementing. That is this variable that's been exported. Okay, so let's first talk about Blink. And actually, I have a pop quiz on this one. So this is a head scratcher, and let's see if people can figure this out. So I have a Blink function here. This one is the one that's running, and this works. And I have a Blink function here, and this one does not work. Question for the audience. Any idea why this one works, but this one does not? And you can see that the second one just spits out a log statement, turns on the LED, waits for a second or so, and then sends another log message and turns the LED off and then waits a little bit more. And yeah, I mean, it's reasonable. This is exactly the same code that's in the other examples. So why doesn't it work here? Why are we doing something different for this one? It's totally pop quiz. So I see we have some alert audience members. Exactly. So the problem is that this one blocks. We're in bare metal. There's no threads or anything. So this one is a spin delay, completely holding the processor hostage. So nothing is going to happen when it's blinking, which means that essentially it's reading 1 character per second. And of course, that totally doesn't work. So
and Keir totally did not get tripped up by this while developing this.
Yes, I promise I did not make this error when I was developing. I should know better, but yeah. Actually, a lot of the Pigweed stuff is used in RTOS contexts, even though all the Pigweed code is bare metal. Most of the projects are using RTOSs. So this would work in that context, but here it does not. Yeah, and I think everyone got this, so it's great. Okay, so that's how this is working, and essentially it's a delay loop. So it counts up until counter max and then flips the LED, but this function returns immediately if there's no flipping happening, and that allows the UART parsing to proceed. Okay, cool. So that's how the blinking works without blocking. And now let's talk about how the RPC stuff is handled. So in this function, essentially, all you're doing is reading a byte, stuffing it into the HDLC decoder. If you got a packet, shovel it into the RPC subsystem. And so that's what this is doing. So this is trying to read a byte, just says, is our byte waiting in the serial driver? If there is, stuff it into the HDLC decoder. Now the HDLC decoder holds state. It kind of incrementally gets packets and accumulates a CRC. And then when it gets a closer packet, it completes, and we'll do the verification of the CRC and so on. If the result is not okay, which actually can be not okay for a few reasons, but one of them is result unavailable or something like that that indicates it's just not finished yet. That's normal, but sometimes you can have not result okay where it's corruption. So that's why I put in a little exercise here if you want to use the Pigweed metric system to track that. Okay, but if it did finish and you got a packet, which is what this is logging, and by the way, you can actually see this. So, oops. So you can actually see it. So as I call, I don't know if you can see, but it says complete HDLC packet. So that's that log statement firing. All right, and now this brings us to an interesting property of HDLC, which is that there's a channel concept, an address concept, and we use it to divide out the log data from the RPC content. So what you're seeing in this window is that these commands are actually running over address 0. It might be a different address, but something that's different than the log statements. So these log statements are running over, I think, address 1. And that's what allows them to be divided. So in this case, we're checking, okay, is this the expected channel? If it wasn't, just log something so that the other side knows, and then proceed. And finally, process the packet. So if everything else is good, send it over to the RPC system. This command, remember, we're in bare metal. So there's no threading, there's no queuing. This is going to run to completion of that RPC call. So if this invokes, in this case, say superloop.getStats, it will run until it is complete. Okay, so I haven't gone through what the actual RPC implementation code looks like before I go there. Oh, okay, yes. Thanks for coming, Benjamin. Sorry, we weren't able to get through everything. Yeah, I don't know if we are going to get kicked out or not. Yeah, we're at time. Let me hop over to the implementation. So this next part is, I'm just showing you what the superloop service looks like. So this is essentially the RPC stub that matches the proto file that was in the earlier, that I showed earlier. So this getStats here is this method here. Now in this case, the implementation is actually somewhere else, and we're not going to get to doing blink control, but that's what this is. So yeah, so this is the file. And the interesting thing here is that the class that matches the service, this generated thing here, using the curiously recurring template pattern, which is not actually that complicated, but sounds fancy, in order to put the RPC methods that are needed into the service. And that's about it. So other than that, it's just a normal class. Yeah. Okay. Now, I don't know if we're going to be kicked off, by the way. I'm happy to go a little bit longer, but I understand many people may have to go. So I'm not sure. Hackaday organizers, is it all right if we go a little longer? Cool. Okay, in that case, I'm going to go a little bit longer. So if people have to head out, no problem. Thanks for coming. So I'll show you what the implementation of this looks like in here. So the other file was the header file. And there's one method that was not implemented, which is the actual RPC method. So you can see here what this looks like. So in this case, getStats is server context, which we're not using in this case, but it lets you do various things like check what channel a request is coming on. And it has an input and output. So the input in this case is stats request. In this case, it's empty. We're not, you can see from here, getStats has no arguments. So there's just nothing. So it's empty. But the response does actually have something. So you can see here, loop iterations is set to whatever the loop iterations were. And so you can see how this works. So in short, this proto is filled in. So stats response is a nano-PB struct. There's multiple implementations of protocol buffers that will work on embedded. We're using nano-PB here. Pigweed also has its own its own protocol buffer library called PW Protobuf. We won't have time to go into it. It makes a different set of trade-offs than nano-PB. But in this case, we're using nano-PB because I think it's easier for this workshop. And so all we have to do is fill in the response. So response.loop iterations, we just assign it. It's just a struct. And then we're done. All we have to do is respond back with status OK. And the Pigweed RPC system will take that struct, serialize it, and then send it out over the wire as a response. And so that's what you're seeing here. Now, if we had a bunch more time, I would go through and build more things here, but I think we're pretty much out of time. So I think we might call it here. So yeah, so why don't we open up the floor to any questions really about anything that we showed today or Pigweed in general. We're here to answer questions. So yeah, what do people think? Any thoughts? Any questions? And thanks everyone for coming. Really excited to have people come and take a look at our stuff. Even in a somewhat early state, it's really great.
Yeah, that would be the one scary thing is like, wow, there's a lot set up in this structure here, like this whole data, this whole like the workshop structure. Like if I wanted to adapt this to one of my own projects, like I'm not sure I'd know where to begin. Like what in here is the stuff I'm supposed to edit and what I'm not supposed to, and where do I define things? I don't know if there's sort of a, you need like a guide, a map guide to the directory.
Yeah, yep, I concur. So thanks for being patient with this. Were you thinking about the RPC example specifically, or just the whole thing?
No, the whole thing. No.
Yeah, that's
frankly
that's
the RPC thing doesn't interest me that much, but like,
yeah. Well, so the idea with the sample project is that it's supposed to just offer like a canned example that has Pigweed put in a reasonable place, and we'll have tests that you can, you can obviously write your own tests, just kind of shows how to do it. Probably what we need to do is, as you suggest, put in, oh, here's how you would add a test, here's how you add a module. And it's true, this is not well documented right now. So yeah, it's good. It's good
right,
feedback.
or if I didn't want to start from that, not that it's a bad thing, but like if I'm going to actually do this for a real project, I'm going to need to take all the workshop stuff out. So that would be like, okay, yeah. Now where do I add? But how do I start afresh, or how do I make it freshly clean?
Yeah. So new project setup is something that, yeah, it's a tough one. So here's the problem. If you make everything configurable, you end up needing a little bit more boilerplate. And if you have more boilerplate, it makes starting from scratch more painful. And so you're in this trade-off space where you have to decide, do you want to pre-can things, which is possible, and then it's relatively straightforward. You just add a submodule, add like 2 files, and you're good to go. Or do you want to make things very kind of easy to configure, and which is what we've kind of done with Pigweed. You end up needing a little bit more pomp and circumstance, I guess, or a bunch of additional steps to get everything going. And so that's what Sample Project kind of reflects. With that said, it is not crazy to copy over just a few things to get it working. You don't actually need all that much. And so you're right, we should probably put together a guide that explains like, okay, here's the core things you need.
Cool. Thank you so much. I got to run. Bye.
Cool. Thanks for coming. Bye. All right. Alex, sounds like you're interested in digging into it, so that's great. Cool. Glad to hear some people might look at it for their projects.
I mean, it's pretty obvious to me that I would want to use it if it were set up for me and I didn't like have to go through the sort of activation energy of figuring it all out. I guess the question is basically his, which is once I get around to actually having a project that makes use of these things and needs them, like, I wonder what the activation energy will be at that point.
Hopefully less. I mean, our goal with the starter project is you literally just fork it and you're done. I mean, you can delete a couple of directories, and if you want, you're good to go. That's the plan. And actually, one of the things I didn't get into is that one of the benefits of having something like the sample project is that we have all this linting stuff set up. So let me just quit out of this. I can show you. I'm not sure if this actually works right now, but probably. So we have this whole pre-submit thing that does all this code formatting and whatnot, and it's all already configured. And this is kind of nice. It takes a little bit of fiddling to get this working in a new repo without putting too many assumptions about project structure. And so things like this they're just nice. Now maybe we could have a reduced sample project that has less in it, sort of just a very minimal set of things. So that could be something that we do. Life cycle state. Okay, great question. Pigweed's early. So right now we have some pretty well-developed modules. So things like the tokenizer, which I didn't go into in too great detail, but that one's kind of interesting. Tokenizer is pretty well-developed. Rpc is pretty developed. The key value store is also pretty developed. The crash handler, there's a bunch of individual pieces that are production grade now. Now the overall thing is still early. So this sort of framework part of Pigweed, the part that's more like this whole system as opposed to just a collection of libraries, it's still early. So we're missing a bunch of things. For example, we don't have RTOS or synchronization primitives. This is something that we're working on now. Hopefully we'll have that in soon. That will allow you to make portable code that does synchronization with different RTOSes. So you can write your code against the Pigweed APIs, which will mostly be standard C++ ones, and then share it across different RTOSes, which we think is exciting. So that's still incoming. Another area that we don't have anything for, and this is a big deal, there's no how, right? If you want to control I2C, if you want to use an ADC, if you want to do a DAC, SPI, we don't have anything for these right now. Now, if you think about the context that Pigweed's used in, which is mostly to kind of slot into existing large code bases, a lot of these projects typically have these facilities already. There's already an I2C interface. There's already a favorite way to do DACs. There's already a system for, even for OS primitives. So that's kind of why we don't have those. And so this more focus on middleware, you just don't need those facilities as much. But they're coming, because obviously it limits the amount of higher level things you can do if you don't have any way to access hardware. So that's coming and is not there yet. What else? Yeah, in terms of development, it's under pretty heavy development. I mean, you can see in our Garrett instance, you can see the amount of patches flying in, so it's pretty active. Yeah, very active development. And in terms of life cycle, I will say that parts of Pigweed are shipping in Google products. That is all I can say. Yeah, so I think that's most of it around life cycle. In terms of like developer experience and documentation, we have some stuff. It's not quite to the level I would like. So things like this workshop are actually really helpful for us to see where people have problems getting their stuff set up and working. So yeah, so that's another area that we've done a bunch of work, but a lot more work is still needed. So yeah, that's kind of where we are in the life cycle. Did that answer the question? Cool. All right, anybody have other questions or thoughts? Okay, great. Well, it was fun to give everybody a tour around some of the stuff in Pigweed. We're really excited to have people using this. Yeah, we're very excited it's also open source. That was some work. So yeah, it's really exciting to share it. Cool. And just maybe before we hop off, just wanted to mention, we do have a Discord chat that's open to everybody. So please stop by if you're interested, or if you have any problems working with Pigweed, or we're there to chat, and we're pretty much there all the time. So come by anytime. All right. Well, I think that's it for the workshop. So thank you everyone for coming. And I also wanted to give a shout out for the people on my team who put in a bunch of time to make this happen. So thank you so much, everyone. This is a great job. I'm really excited that we were able to put together this workshop.